So in this lecture today, not lecture, it's just this is the part 2 of tensile testing, where we are going to understand that how to analyze the tensile data. So this is the data which I sent you, and usually this is what you will get when you do a tensile test. And unless you are using an extensometer, and you will see what an extensometer is when we do the low cycle fatigue testing. So that's a sophisticated machine which will take some time, and so the point is, if you have an extensometer, then you will get another data here which will be giving you the strain in the extensometer. I hope that this screen is visible. It should be okay. So fine. So usually we have these data, and usually we have load and displacement data not only in tensile testing, but we also have this same data in compression, in 3-point bending. So in 3-point bending, whether or not it's a fracture toughness testing or it's just a flexural testing, which we don't do in metallurgy. So in mechanical, people do 3-point bending for an uncracked specimen, which is just called bending test or flexural strength, finding out flexural strength. So that is basically just this thing, and you hold it like 2 pins are there. So the two pins, they hold the specimen like this, and there is another pin which presses. So you see there are 3 points, and this is why it is called 3-point bending. You can have 4-point bending also. So in all those tests, you will get these data. In fatigue testing, you get these data only, but you also get something else which is different from this. Okay, so the point is that analyzing these data, what we are doing in tensile test, can help you in many other tests. So here what we know before starting the test is that the initial diameter of the specimen, which I think I mentioned was 4 millimeters, and the gauge length, which was 20 millimeters. So and then there is other important information which you must have, is what was the loading rate. So usually in the machine you have a ramp rate, so by what amount the displacement is being applied, and that is given in the form of, let's say it is 0.5 millimeter per minute. Okay, so using this and gauge length, you can calculate what is the strain rate. We will do that sometime later, but for now let us calculate first we have to calculate the area, initial area. So let me write initial area, and that is it, I think. So that will be pi r squared. So r would be 2, so 4, right? So this is how much? Yeah. So this is millimeter squared. This is my initial area. Now I can calculate engineering. So let me just write engineering stress, and that will be equal to the force divided by initial area, which is 12.57. So this is in Newton per millimeter square. You should always keep on checking the dimensions. So Newton per millimeter squared is already megapascals, and you see Microsoft always does it, so it always changes the P to small, so you have to deliberately change it back to capital, because Office thinks that it's a word, and so only the first letter should be capital, but it's not just a word. So So you must always be having M and P capital. That's the standard way. Okay, so now this is my engineering stress. What will be my engineering strain? And engineering strain will be the extension divided by, so extension is basically delta L divided by the initial length, which is gauge length. So that is that. So we can do this calculation, or we can first smoothen this data. Okay, we can smoothen this data and then we can do it, because this data I think is too much. I think it is 7,500. That is not too much, but sometimes you can have too huge data. Depends by what frequency the machine is recording. So you can have different ways of smoothing the data. I will use a very lazy way of doing it. So I'll just put some colon C. Actually what you can do is you can read the whole file using any programming language, Python, MATLAB, whatever you are comfortable with. But I will not do that. I'll simply copy it and I will just run it in MATLAB command window. I hope the computer isn't dead. Yeah. So what I will do is I will just say that YY. This is actually load. No? This is displacement. I'll write XX is equal to control V, and the machine will now hang. And I will remove the last. Oh, I don't think it will do it. Okay, so I will just write 0 and is it writing 0? No, it's not moving. Oh, it collapsed. No, it's there. But it's kind of dead. Okay. Oh, now it's there. I think what happened? Just nothing happened. Anyway, so what we can try is I will just. But I wanted to see if it works. Because. Okay. So I don't want the colon on the last point. Neither here nor there. And so let me copy all this and put it back. XX equals, and then I will at the end I'll put like this and colon, and inside I'll control V. So it says it's busy. And I think it collapsed again. So I don't think it is going to work like that. Maybe if we, it depends, probably my machine is not good enough to handle this much data. So I think, let me write it in a program and let me see if that works. Okay, so XX is equal to colon control V and this, and YY is equal to, now in YY I will put load. So basically this is the code which can be used to smoothen the data. So I have put all the force and displacement values in XX and YY columns, and you can use this function. So low s is the algorithm. There are different algorithms using which the data can be smoothened, and then downsample function is used to, so this is an inbuilt function, and this is used to downsize the sample. So first data point and then the next data point will be taken after 25 datas. So this is how you downsize the sample. But this code will work if you have the signal processing toolbox in MATLAB, which I don't have, and this is why it is not working. So just the downsample part is not working. Apart from that, you can see I have YY1 and XS1, although of the same sizes. So let me show you how it looks like. So plot, and if I just plot the older data, XXYY, as circles and no lines, and if I plot it, then so it looks like this, the data, and this is too much data, that's why it looks too dense. And on the same, if I plot the smoothened data, I don't think there will be any comparison possible, but why not? So instead of XX, I have to write XX1, YY1, and here I'll just write R plus or R line. So it will be a red dashed line. I think the syntax is right. So if I just do it, what happens? So hold on will simply, oh, this is not correct. So XX1, YY1, is it a, I think XX1, YY1 both are same because my syntax is wrong. So why it is wrong, I do not know. I have changed the XX to YY position, even then it is okay. So okay, so I just need to remove this part and this part here and rerun it. So can I undo it? I don't know. I will just close this one, and but anyway, this is not going to work. So meanwhile, because I don't have that toolbox, so meanwhile I will show you another way of doing it. There is another software which is called Sigma Plot, and in Sigma Plot you can just instantly do it. So yeah, so what we can do is we can use Web Digitizer or Web Plot, just a second. So I think there was a Web Digitizer, which is, now there are too many. A Web Plot Digitizer, I do not know if this is that. It looks like that. Okay. So here what we do is we simply can take a picture which doesn't have too much data. So again, you see I'm getting the same error because of the toolbox, so that is fine. I just wanted to show you how it works. So let me just copy all this and paste all this and see. So you see now you can see. So smoothened data, the red dashed line exactly falls on the previous one, but if you use the down sample, then you can choose this, plot. So what I will do is I will just take this picture and I will save it. So can I save it, or I can use my local saving tool, which is snippet. So cancel, and where is snippet? Snippet new, and I take this one, and then I file, save as, and I put it on desktop, and I put it here somewhere in the, and here I put tensile data. And then how do you use this web digitizer is that, so launch now, and I think this one will be easier. So here you have to load the image, and so how do I load the image? File, load images, choose file, and then I go to Weaver here somewhere, and this is the image, 2D of course. So align axes, proceed, and here what I have to do is I have to choose the levels on the but this I don't know. Anyways, so basically I have to choose 2 points on x-axis and 2 points on y-axis. So I'll choose 1 point here. It could have been better, but I'll choose 1 point here, and another point is, so let us say if it is 6 here, I think, can I undo it? Okay, so file, load images, choose file, and take this file, load, align axis, and proceed, and let me take 1 point exactly here. So here, and another point. So you should take 2 points as far away as possible. So let me take another point here. Let me take point for, so what I have chosen for x-axis is 0 and 6. For y I am choosing 0 and 7,000. 0 and 7,000. Okay, so I'm done, complete. So x1 point was 0, point 2 was 6, point 1 was 0, point 2 was 7,000. But yeah, I think it should be okay. It is not a logarithmic scale, so I'm not checking those values. Assume axes are perfectly aligned with image coordinate. Skip rotation correction. Yes. Okay. So now I think it has been calibrated. I just need to choose some points. I'll choose the red dashed line which I drew, but instead I'll just select some points on the curve. So let's take this one, here, there, here, there. Now here is the part where there is non-linearity starting, so I'll select a lot of points here so that I capture the non-linear zone in a precise way. And actually the better option would be to use Sigma plot software, but you can also use some of the coding to decrease the data just like that. So you can just say that next n terms are 0, So that also you can do. I'm taking a few points which are actually not good. But anyway, so now I have selected some points, and now what I do is I save the data. So I see view data, and this is the data which I'm getting, and then I download the data in the .csv file, and then I can simply import that data in a different sheet. So go to data from text, and I go to, I think it should be in download somewhere, or I think it should be there only, no? It is in download. The name is default dataset. So where is it? Default dataset. And here's the data, and the separator between two values is comma. So I'll go to delimited it, and then I'll use comma and finish and OK. So this is my data. So this is my displacement data, and this is my load data. Okay. So now let me plot this and see how it looks like. So you see I have only 73 data now instead of 7,400, and it looks more or less, it captures the curve which I had. Right. Now we are coming to the serious problem, that usually it is expected that the data here should be linear, because this is linear elastic region, but you see there is a small non-linearity here, right? So now we have to talk about machine compliance, and what is machine compliance and how do we correct it. So that I will tell you, but let me do the part of analysis now, and then we will come back to theory maybe in the live session sometime, or maybe in a recorded session which will explain this. I believe we can have a live session maybe in the next week sometime, where we can talk about the machine compliance part. Okay. So the problem is there is in this strain there is a contribution which is coming because of the machine itself, because machine is applying load on the specimen. Sorry, I do not know if I was audible so far. So machine is applying load on the specimen, and because of that load, machine itself is getting elongated, right? So how much the machine is getting elongated can be calculated using machine compliance. So that part we will do. Okay. So but before that, let me just write the engineering stress strain part. So that was here. I'll just copy it and I'll paste it here. So we have to insert something and put it back there. What is this? Now this is, so here I have to write the value of load, which is this, and here I have to write the value of displacement, which is this, and now I have the, so now I have this engineering stress strain values. Okay, and now this strain is actually, total engineering strain is equal to the strain because of elasticity plus strain because of plasticity. Okay, and this strain elastic is actually comprising of two parts, because the strain elastic is equal to elastic strain because of the sample plus elastic strain because of the machine. Okay, And machine part we are not interested in. We want to know the elastic part of the specimen only. In order to find out that, in order to remove that part, we need to know the machine's elastic modulus, which we don't, right? And if some of you has calculated the Young's modulus, you must have found out that to be a very small value. So we can check that. But before that, we have to remove the non-linear part of the specimen, that also, so which is called zero correction. So the first thing which we have to do is zero correction, and I'll tell you how to do that part. So let me insert a few columns here and let me plot this. So insert in a, so this is coming opposite. I don't want this thing, or maybe no, it doesn't matter. I'll just remove that. I'll take this up here, and I want x-axis to be this and y-axis to be that, and let me write engineering stress strain. Okay, so this is how my curve looks like, and there is a little bit non-linearity at the end, right? So I want to remove that non-linearity. How do I do it? I have to select few data which fall in the linear elastic region. So I can see that from 200 to 400, it looks like the data is linear. So I will just take the data between 200 and so I'll just remove some of the data and then I'll put it back, don't worry. But here I want to do what is, I want to select data between 200 to 400 for the stress value. So 200 to 400, so x value, so I can take it actually from here and to 400, so 405 I can take, no issues. So these data in x-axis, so I'm taking from row number 10 to 15, and then row number 10 is this one, to 15 is this one, and this is what I get. This is what I get. I still, but maybe that is because of the selection. Now I will linearly fit it and display equation on chart, and this is what I get. This is the equation which I get if I linearly fit it, right? So this is the slope of the equation, right? And the intercept, if it was straight going to origin, then the value would have been 0. So it should have been y is equal to mx, but this equation is y is equal to mx plus c. In this case, the value of c is negative. So what it means is that the intercept is not on 0. It is intersecting y-axis somewhere else, right? So where is it, where this line is going to intersect the x-axis? That is what I am interested in. So if I put y is equal to 0, then x will be simply minus c by m. So that will be negative of negative 92.996 divided by whatever is the slope. Okay, so one more important thing is, you see what is the slope of the linear line, which is approximately 20,000 megapascals, and that is not the value of, is it megapascals? Yeah. So that is not the value of metallic materials Young's modulus. So this is a steel, and for this steel, usually the steels have elastic modulus of 200 gigapascals. So we are getting 20 gigapascals. So that is approximately 10% of what you usually have, and this is happening because of machine compliance. Okay, so if some of you have calculated the Young's modulus, you must have got a value which is closer to this 20 gigapascals, and that happens because you know we are measuring the displacement or the strain which is comprising of the strain from the machine also. So that's the reason. Now, so this line, if I extrapolate to x-axis, it will cut somewhere at a non-zero value. I want to shift that to zero value. So how do I do it? I will have to remove the x-intercept from the x value in the data. So x value is the strain, and from this strain I have to remove the value of C by M. Okay, so I have to remove the value of C by M. So what will be my value of engineering strain zero corrected, or origin corrected also, but usually call it zero corrected. So this is the value of x minus, and now I have to write minus 92. No, actually I have to shift it in the opposite direction. So minus 92.996 divided by 19916 is the slope. So this will be this. Okay. So this is now zero corrected, and let me plot the both values, which you will see how it differs. So let me plot the non-zero corrected value over the zero corrected value. So here I will just write raw, and I will add another engineering stress strain zero corrected, and the x values will be this new column F, and this will be the stress value, which is that. Okay, and I remove the trend line because I don't want it. And now you see that this line, the straight part of this line will be hitting zero, but some of the line are getting on the negative side, and that part we don't want because that is coming of the initial non-linearity. Why this initial non-linearity comes is because sometimes the threaded are loose, so they adjust, and sometimes the thread slips. If it is a grip, it slips. So because of that, the initial non-linearity comes, and that part we don't want. Okay, so the red data is the shifted data, so that the linear part hits the origin straight. So now our strain is zero corrected, and now I want to remove all the elastic part. Why I want to do it is because the elastic part is having the contribution from the machine. So the strain from the machine is coming in the elastic part of the sample and not in the plastic part, because machine is not going to get deformed in plastically. Okay, because machine has a higher surface area, and we are applying a load which would not cause any stress higher than yield strength even on the grip zones of the tensile specimen. Forget about machine. So we can deal with machine compliance in a different way also, which we will do in a different session in the next week. But for now, let us remove all the elastic part, all the elastic strain from the data. So here I will just write plastic strain, and plastic strain would be simply this zero corrected value minus whatever is the stress value I have got, divided by the slope of the linear part of the curve. So that was 19916 approximately, I think. I'll have to check how much it was. 19916, yeah. So now what I have removed is the elastic. What will be the elastic part? The total elastic part, that will simply be sigma divided by the slope of the curve, right? Because sigma by E is the strain, is the elastic strain, and in this case E is inclusive of both the machine strain and the sample strain. So now if I do this, I only have plastic strain, and if I plot that one on over this, so let me write it: engineering stress and plastic strain, and the x values will be this and the y values will remain the same. And now what I want to do is I want to change the lessons. So now you see what is happening actually. So not like this. So I go to the stress strain raw value and draw it as a line, and let us remove any marker, because now you have seen how it looks like. So I'm just changing those to different lines, and after shifting, after removing all the elastic strain, you see that the curve becomes straight because the inclination in the stress strain curve is because of the elasticity, because the stiffness is not infinity. So once you remove the elastic part, it becomes straight. What does it mean? It means that any finite value of x-axis will start only when the yielding has started, right? So now if I also add a line to my third curve, which is a solid line there, and it shouldn't be that thick, and let me use this one and color red. So now, and let us not use, let me remove, but actually that is, but let me remove the, but no, it's okay. So here I can actually magnify this, right? I can magnify it by changing the axis. So actually I have to capture between somewhere between 400 to 600. So vertical axis, so 400 and 600, you see. So it is somewhere starting here, and this value is how much? This, oh, okay, I leave it. So if I just put it on this one, it is 493.33. So somewhere between these two is the yield strength, because that's where the finite strain is coming. Okay, so 493 and 508. So somewhere in between that will be plus 508 divided by 2. So somewhere approximately 500.5. So 500 megapascals would be the yield strength of the material. So now let me change the values of the axis to its normal values. So 0, and the vertical value 0 to 700. Yeah. So the green one, the last one, is the plastic data, and from that I can estimate the value of yield strength to be 500 megapascals. Okay, and then you can do all the things. You can find out the maximum value, which will be UTS, which will be 600 something. So that I can simply write it as max of the column of stress, and that value is 665. So this is my UTS value, and so then you hit this value 665.67. So 665.67 is somewhere in between. So, and from there you draw the horizontal line. So you get the uniform plastic strain, add the elastic part to it, so you get the total uniform strain of the material. And then calculation of true stress and strain is straight away using the formula. One thing you should know is that You shouldn't calculate true stress, true strain beyond UTS because those formulas lose their validity. After UTS, they are not applicable because the volume is not constant anymore. The density is not constant because there are voids coming up inside the material. Okay, so this is how you analyze this, and so I will close this session now. You can use what I did to reanalyze the data and then put the plot, the end part, and whatever you understood from this analysis part of the tensile testing in your report in the corresponding appropriate sections. And please use the data with, so when you plot it, you plot everything with the legends. So I want you to use legends, and each legend should be indicative of what they are. And so you can do it in a very nice way, because looking at a plot is something which you don't want to make bad. So here you can use axis title, and you must name it stress, and you should write stress, not engineering, because you will be plotting true stress also, right? And here you write strain, and you can change the color of this, or also font and everything, make it a little bigger, and this one also black, bigger, Times New Roman. This also you can make black, this also you can make black, and here you can change the major minor axis to a different way, and you go to here, you make that also. So I think this should have solid fill. Oh, line was not required, but solid fill was required. So something like this, and then this looks a little escalated, but now it is okay, and it doesn't look good, so I should also have a solid line. Yeah, so this is how you should plot and put it in the sheet. Okay, thank you.